Neural networks are one of the most powerful machine learning algorithms, and today we are going to mention how learning is handled in neural networks. Learning is handled by backpropagation algorithm. It's called backpropagation because prediction is applied from left to right. On the other hand, learning is applied from right to left. Reverse direction of the prediction, learning or training. We would propagate backwardly from right to left. And learning in neural networks is actually based on updating all of these weights, and this algorithm decides these updating ratios. For example, this is supposed that this network produces net output y output as prediction, and suppose that it should produce actual as expected. This means that network made an error. Network made an error in ratio of actual one minus prediction net output y, and mostly mean squared error used as a error metric. In this case, we need to calculate the power of 2 of this difference and over 2. Mean squared error is common because it's derivative in simple form. Now the question is that how much this calculated error should be reflected to, for example, W15. This question also refers to calculate the derivative of total error with respect to the W15. Similarly, how much this error should be reflected to W12. This means we need to calculate derivative of total error with respect to the W12. Now we will mention these calculations, and I have extracted the related pieces of W15 backwardly from right to left. W15 connects a H5 unit to Y unit STM, and we need to calculate the derivative of total error with respect to the W15. Here chain rule will help us, and I will write it here. Chain rule says if a variable z depends on variable y, and variable y itself also depends on variable x. In this case, variable z depends on x as well, and we can show derivative of z with respect to the x like that. This calculation also can be expressed as derivative of z with respect to the y times derivative of y with respect to the x. This is chain rule, and we will apply this chain rule like that. Before that, every unit serves activation function. For example, suppose that we will apply sigmoid function as a activation function. In this case, input would be changed as 1 over 1 plus e to the power of minus x. And we will apply chain rule for this calculation like that. derivative of total error with respect to the net output y times derivative of net output y with respect to the net input y and finally derivative of net input y with respect to the W15. Let's calculate all of these calculations. For example, let's say 1, 2, and 3. Before that, I need to clear this here. Give me a second. For number 1, I need to calculate. Sorry, please remember that error was actual minus net output y squared over 2. Then derivative of error with respect to the net output y would be power 2 comes to the beginning times actual minus net output y, power would be 1, and the derivative of the term in the parentheses would be minus 1, because derivative of minus net output y would be minus 1 times 1 over 2. Calculating 2 and 1 over 2 would be 1, and here net output y minus actual is the result of first number of equation. Let's calculate number 2. Again, this unit applies activation function, and we suppose that sigmoid is the activation function for this example. Please remember that sigmoid function is 1 over 1 plus e to the power of minus x, and derivative of sigmoid function would be y times 1 minus y. You can watch sigmoid lecture. I have also published it. Based on this rule, derivative of net output y with respect to the derivative of net output y with respect to the net input y would be net output y times 1 minus net output y. And finally, equation for number 3. Please remember that W14 and W13 is connected to this unit, and here H5, H4, and it's the bias unit is connected. I mean that net input Y is calculated as W13 times 1 plus W14 times net output H4, net output H4 plus W15 times net output H5. Now I need to calculate derivative of net input Y with respect to the W15. Then this would be derivative of this term is 0. After that, derivative of this term would be 0 too, because it's they don't depend on W15, but this term depends on W15. That's why derivative of this term would be net output H5. Net output H5. We have calculated all of these three equations. We need to multiply them. First one is net output Y minus actual. That's the number one's result. Then number two's result would be net output Y times 1 minus net output Y, and times result for equation 3, that would be net output H5. That would be derivative of total error with respect to the 15. Notice that we can say all of these terms as sigma H5. Sigma H5 times sigma Y times net output H5. I save this screen. After that, we need to for example have to change W15. It would be like that. W15 is equal to W15 minus alpha times, for example, alpha can be 0.1. It's a small number. And this one, derivative of total error with respect to the W15. we can also for example, here I have extracted related pieces for W12. In this case, again, we need to calculate derivative of total error with respect to the 12. We can apply chain rule here, like in our previous example. Derivative of total error with respect to the net output y, NOY, I say. After that, derivative of net output y with respect to the net input y. After that, we can jump here. Derivative of net input y with respect to the derivative of net output h5. After that, derivative of net output h5 with respect to the net input h5, and finally derivative of net input h5 with respect to the W12. We can calculate all of these equations like in our previous example and multiply them, and after that change the W12 like that. W12 is equal to W12 minus alpha times, you can say 0.1 for alpha, and derivative of total error with respect to the 12, and all of these multiplications would be derivative of total error would be a derivative of total error with respect to the W12. So in this video we have mentioned the math behind a backpropagation algorithm. It can be evaluated as complex, but if you understand the concepts, you can apply it in practice easily. Thank you for watching, and see you next time.